Hello, everyone. So I'm very happy to be able to give a talk today in the Monte Carlo seminar. I've always been watching videos on YouTube for this seminar series, and I'm a huge fan. And today it's really a great honor for me to present here. So today I'm going to talk about diffusion models generalization about data-dependent rich manifolds. So hopefully my talk can include stuff that people in the room or people online will feel interested in. Yeah, so first I would like to send to my wonderful collaborators. So this work is a joint work with an undergraduate, Yitong Cho in USDC, and who is going to be in the United States in the next fall as a PhD student. And also with my wonderful postdoc mentor, Mo Tao, who is currently a full professor in Georgia Tech School of Mathematics. So in my talk, I'll basically follow the roadmap as displayed in this slide. So I'll start from the motivation, which is why are we interested in understanding generalization of diffusion models, especially what does a non-memorizing diffusion model generate? And then I will go to the problem setting to help us to set us on the same page about notations and mathematical framework. And after that, I will talk about related work, which also motivates our core ideas in this project, which is the geometric object log density regions. And after that, I will talk about our results about inference dynamics and training to geometry link between inference and training. At the end, I will show some experiments and talk about the takeaway and limitations of this work. So let us start from motivation. Why are we interested in generalization in diffusion models? To understand that, I guess the first thing I want to explain is what is memorization versus generalization in diffusion models. And I like this picture in Sompali et al.'s 2023 paper, which is a very intuitive way to understand memorization versus generalization. So in this picture on the right-hand side, we have 3 rows of pictures. And for each picture, you can understand it as a data point or a data in diffusion models. In the first row, 5 pictures represent 5 training data of your diffusion model. And the second row basically represents what you could have when your diffusion model memorized. So basically, you will generate exact or very similar pictures as your data pictures. And the third row, which represents what happens when your diffusion model generalizes. So you still generate 5 pictures, but you see these 5 pictures are no longer similar to the training pictures. Even though they are not the same or similar, they are similar in some sense. For example, if you look at the sports car in the training data, and then you refer to the corresponding, you can easily refer to the corresponding image in the generalization data. It's still a sports car, but it's a sports car in different style. And also, generalization can make your generalized picture richer. For example, this is the lamp. And here in the general picture, you will have a lamp, but you will have some more furnitures. For example, we have this sofa here, right? So you can really see the difference from high level between the memorization and generalization diffusion models. And the key question that we want to understand is when a diffusion model is not memorizing, so how or where do new samples differ from the training set? So for this, we need to understand for this part, we need to understand why diffusion model is powerful. It's powerful because of it can generalize, because we don't want to replicate our training data. We want our diffusion model to generate something new, something novel. So which means generalization is the more interesting behavior that people want to understand in diffusion models. And in particular, we want to understand like how or where do diffusion models generate new samples. And this is quite important from the perspective of distinguishing between generalization versus hallucination. So for example, here, this is small experiment done in ISO et al.'s 2024 seminal work. So again, we have several pictures to illustrate data. On the left side, the 4 data are from the training samples. They're all data pictures of hand. And on the right-hand side, the 4 pictures are what you can have from a generalized diffusion model. So they are not replicating samples in the training set. They're brand new, but you can still tell the difference between these generalized samples. For example, for the 2 images on the left with blue box, they are considered to be the generalized samples, which means they are good in the sense that you see they are actually real hands with 5 fingers. However, if you look at the 2 pictures in red boxes, so they are considered to be the hallucination, which means they are bad generalized samples because you can see they are not actually real hands. They have more than 5 fingers, like this one have 6 fingers and this one also have 6 fingers, right? So if we can understand like where diffusion models generate these new samples, then we can distinguish between good samples, which is generalization, and bad samples, which is hallucination. And this can help us to access our downstream tasks to make them more reliable. Okay, and next I will start talk about the problem setting and related work. So in this project, we consider a very specific problem setting, which is to summarize, in the inference process, we consider the variance preserving SDE setting. So where you are in your forward process, you are transform your data samples to isotropic Gaussian, and your reverse process, you just transform back using a reverse SDE. Although there are many other settings in diffusion models or score-based generative models like flow matching, like probability flow ODE, things like that. But as you may know, there is a unified way to view all these different models, and then you can sort of transform between different inference processes using time change. And for the training setting, in our work, we actually consider a slightly different training setting. Traditionally, people usually consider you want to learn the score about noisy score matching. And in our work, we consider learning the posterior mean rather than learning the score. And the method to learn the posterior mean is referred as the denoising mean matching. So to get into more details as well as introducing notations, so in the inference process, the 2 SDEs the forward process is this OU process, which is easy, and you can easily write down the solution of this process. And we will use PT to denote the distribution along the forward process. And your backward process is this capital YT. And we will consider early stopping this backward process, and the early stopping times is denoted as this delta parameter. And in this backward process, we know it's exactly in distribution the same as the forward process if you evaluate the reverse time. And this figure just illustrates how your forward process evolved from the data distribution, which could be multimodal, to your isotropic Gaussian, and how the reverse process could transform back to the data distribution. And you can see here I'm simulating 6 passes. So although the distributions are recovered, but the locations of your actual generated samples are actually different. So if you look at the points on the left and the points on the right, although they are following the same distribution, but the locations are different. And we look at the backward process. There's one particular term which is referred as a score function, which is this negative log of density. So this term is the most challenging part when you try to simulate the backward process in order to generate samples. So usually you have to learn this term using some neural network structures. And in general, if your learned score is represented as this S sub theta, then in the actual diffusion model, you are simulating this reverse process with learned score in order to generate your final data. And also the initial condition in this simulated reverse process is always chosen to be the isotropic Gaussian. And the score term is what relates to the training part in this problem setting. And now I'm going to talk about how we train to learn this approximate score function. So the traditional way is called the denoising score matching, where you start from this score matching loss, which is like the weighted L2 distance along the trajectory from this learned score function to the exact score function, right? And unfortunately, this loss you cannot evaluate directly and optimize it. So you have to use some techniques related to the conditional expectation. So if you use the fact that the forward processing distribution can be written as the combination between scaled data distribution and the scaled independent Gaussian noise, and here the two scalars is denoted as A sub t and H sub t, which we'll use in the later presentation. So if you use this relation along with the conditional expectation, you can rewrite the score matching loss as the denoising score matching loss plus some absolute constant. Then rather than optimizing the score matching loss, you turn to optimize the denoising score matching loss. And what's good about the denoising score matching loss is you can evaluate this directly using IID samples from the data distribution and IID noises. And if you look at this denoising score matching loss, you will notice that this is actually what you actually do here is try to predict the noise. You are learning the score function in order to match with this scaled noise, right? So we call this predict the noise type of loss function. And recently in Li and He's work, they will try to argue from the empirical side that when your data has some low dimensional structure in the high dimensional ambient space, predicting noise is numerically not good. So for example, in these figures, you see your data are concentrated on this spiral shape and the ambient dimensions increases from 2 to 512, right? And the ground truth is in the first column. And when you predict the noise, what the diffusion model generates is in the last panel. It's in the last column. And what's in the middle column is when you try to predict the data directly. And you see, like, if you predict the noise, usually when the ambient dimension is high, you cannot really capture the low dimensional data structure efficiently. However, if you try to predict the data, and directly you can sort of recover or generate the data structure more efficiently. So this is what motivates us to consider a different way, loss in our problem setting. And this different loss is called the denoising mean matching loss. So the final expression of this denoising mean matching loss is given in the box here. So it's still a weighted L2 loss, but it's a loss that predict the data itself. As you can see, M is some parametrized posterior mean, and you are trying to learn this M in order to predict this scaled data, because X0 is our data, follows the data distribution. And the way we construct it is simply to utilize the Tweedy's formula. So by using Tweedy's formula, you are able to represent the score function as a linear term plus a scaled posterior mean. And this M is the exact posterior mean. And by doing this, you are able to rewrite this score matching loss as the mean matching loss. So they are mathematically equivalent. And when you look at this mean matching loss, essentially this loss is asking you to do weighted regression along within the time interval from delta to t. You try to learn this exact mean loss, exact posterior mean. And the mean loss has the same issue as the score matching loss, which is you cannot evaluate this loss directly. So then you apply the same trick, you use this formula for xt and you take the conditional expectation, then you are able to derive this denoising mean matching loss, which is mean matching loss plus the absolute constant. And then we were trying to optimize this denoising mean matching loss in our work. So to summarize the setting, So we consider the reverse process, which is this one, and the score term is written as the learned mean matching loss, and uh, it's written as the learned posterior mean, and this posterior mean is learned by optimizing this denoising mean matching loss. So this is, and the goal, our goal is to understand the geometric difference of the distribution between this reverse process y tilde t at the end of the simulating time, which is the distribution of y at time capital T minus delta, and the and we compare it to the distribution with the data distribution x0. So we want to geometrically understand what is the difference between these two distributions. So any questions so far? Okay, so if this is good, then
Can I quickly ask a question? So,
yep.
uh, so from the description, it seems you're in a way retrain your own diffusion model, but I think the original purpose is to understand the generalization of, I imagine, the current like popular diffusion models in the market. So I wonder if you can explain like what motivates you to alter the training process and start to build the diffusion models from scratch instead of just analyzing the existing pre-trained models.
Yeah, so that's actually a good question. So first, I would like to clarify two things. So you mentioned pre-train and retrain, post-train or retrain. And so this is actually not related to pre-train and retrain. So we still train the diffusion model once, but we are choosing a different loss function. And the issue between and whether this loss function performs the same as the other loss function. So this is arguable. This is what's arguable. So mathematically, they represent the same thing if they're exact. But when it goes to training, they could be different.
Mm.
But one thing you will see later is, so this is not our analysis really actually does not depend specifically on this posterior mean matching loss. So you can do the same analysis on the denoising score matching loss because the core object is also well defined there.
So maybe do you expect, for example, the conclusions that you can draw from your current analysis and the training also generalize to maybe understand the existing huge like diffusion models that are currently used in practice?
Yeah, I think that's our motivation, right? We want to analyze the practical diffusion models. I think it is possible, and but there's a lot of challenges from different perspectives, as you will see when I introduce the related works. But I
Great.
think our work does provide a framework that I personally believe could be extended or be improved to analyze the practical diffusion.
Yeah, thank you so much. Yeah.
Okay, so now I'll proceed to related work. So I will try to talk about a few perspectives, understanding generalization and memorization in diffusion models. And I'll also introduce some related works, but unfortunately, I could not mention all of them because there is a huge amount of literatures studying this. So I want to start from the empirical analysis in Iso et al.'s seminal work, because they actually empirically bring some geometric uh, quantifications for the generalization in diffusion models. For example, in this first image, they will try to test on data where are on grids in 2 dimensions, and they found that the diffusion models turn to interpolate between those grid points in a certain manner, and which means generalization happens to interpolate between the data, right? And they also extend their analysis to this hand more practical example to say, okay, the hallucination is because your interpolation is jumping out of the support of your data distribution, while good generalization means you are interpolating within the support. So this set a tone of our analysis. So we want to, if our analysis could explain what they found in their empirical work, it just verifies that our analysis is a good way to start, and it's possible to extend to more practical data. And there are a lot of analytic work that try to understand generalization in diffusion models. One perspective is generalization arises from errors. So if you think about from the countryside, if the learn score is exactly the empirical data distribution, meaning that your score is a gradient log of the density, where your initial density is just an empirical data distribution, then your diffusion model would always memorize, meaning that at the end of your generated process, you will replicate the data points with equal weights. And this is almost never happening in practical diffusion models because there are errors when you try to learn the score functions. And one line of literature is to quantify these errors from different sources. For example, in one of our previous work, we're trying to evaluate different sources of the errors in diffusion models and eventually obtain a bound to quantify the general distribution from the data distribution in terms of KL divergence. And as you see in this arrows, you will have the initialization arrow, you will have the discretization arrow for the inference process, and you will have arrows from training, right? And usually this initialization arrow and discretization arrow can be easily controlled to make very small when you control the inference parameters. For example, you simulate more steps, you choose smaller step size. But the training arrow is really the bottleneck in practical diffusion models because you have complicated data, and if your if your network is not large enough, you will not be able to control this training arrow to make them very small. So arrow like almost always exist in diffusion models, which make them generalized. And another line of work is trying to focus more on the training part. So they try to understand when your training can generalize and when your training can memorize from the statistical learning perspective. And these are two recent work which somehow attack this problem from a very similar direction, which is they study the training under the random feature network. So they consider slightly different optimization dynamics, but their network are always the random feature network, and they analyze the training loss and the test loss in the asymptotic setting, where your data, the number of data, which is the n here, and the number of feature, which is the parameter p here, and the Monte Carlo noises, the number of Monte Carlo noises m all goes to infinity under a certain regime. And they were able to discover, find regimes that will distinguish between memorization and generalization of the diffusion model. For example, in the first work, they show that when the number of features is increasing, which means your network can have better ability to represent the score, then you can learn the score well, which would lead to memorization. And when the number of features is smaller than the number of data, you cannot efficiently represent the score, then you would have non-negligible errors, which lead to generalization. And in the second work, they have a final analysis that further distinguish two regimes in this generalization, which is one is the architecture regularization, which means in this regime, the architecture bias dominates. So that means your training dynamics actually is good enough so that your training error is small enough, but what dominates this training error is the architecture bias. And the other country is when the training dynamical error dominates, which means your network is good enough. You have enough number of features to represent the score. However, the optimization dynamics is not good enough in order to find the global minimum of the loss function. And the third line of work I want to introduce is from the geometric perspective, which is which is closer to what we want to do. So this geometric perspective usually assumes some manifold hypothesis, assuming the high dimensional training data are around the low dimensional manifold, and assume there are some specific structure of the training arrow. They show that generalization is likely to happen on or around the manifold. And there are a few works that study along this direction. For example, the first one studied the simplest case where you only have 2-point data, and they were able to show the generalization would interpolate between the 2 data points when the training arrow is of specific type. And the second one, they basically argue it's easier for you to learn the score that can represent the support of your manifolds. And it's harder for you to learn the score that can represent the whole landscape of your data distribution within the manifold. And the last one is also a very interesting work. And what they argue is when your score arrow is a kernel type of arrow in the log space, then if you simulate the diffusion model, you would be able to discover this kind of interpolating structure on the data manifold. So, for example, when your data are around this heart shape manifold, then your diffusion model would generate samples that fill out this heart shape low dimension manifold. Right. So to summarize these perspectives, I will use this triangle shape. So if you want to understand generalization, there are a few things that you have to consider. One is the data geometry, one is the training dynamics, and one is the inference dynamics. And if you look at the works that I have been introduced, for example, the error estimation line of work, it sort of can bridge training and inference. So you can quantify all the errors from training and inference and eventually give an error estimation at the end of the inference. And if you look at the random feature, the training loss test arrow, that line of work is trying to connect between training and data geometry, but not quite, because they can sort of consider the data, for example, the number of data, and relate that to the training, especially the test arrow and training arrow from training, but they cannot actually reflect the geometry of the data. And the last line of work is trying to bridge the data geometry and the inference. Assume your data has geometry and assume certain type of training arrow. You can study, like at the end of the inference, what is the geometry of a generated distribution, right? But and our work is basically motivated by our understanding to this line of works, and we were trying to build a framework that can analyze the generalization out from the data geometry directly. So the way we do it is we start from the data geometry. We introduce our core object, which is called the log density ridges, as an anchor geometry that we can study along the inference process. And then along the inference, we study the relations between that anchor geometry and inference, and we introduce this rich line slide picture to describe the 3 stages in inference, like different relations between my inference process to this anchor data geometry. And at the end, we study how this data geometry affects training. So we relate the training arrow, we impose a training arrow decomposition under specific training model and training augmentation dynamics, and we relate them to the data geometry. So now, so this is just a rough idea how we formalize our framework, and now I will fill in more details about the framework starting from the data geometry. So first, I would like to talk about what is the data distribution that we consider. It's actually slightly different from traditional literature. Traditional literature, they usually consider the data distribution to be a population distribution, which means the distribution has to be smooth. It could be supported on manifolds, but it has to be smooth on the manifold. But in our work, we basically treat the data directly. We consider the data distribution to be the empirical distribution from our raw data. And all the assumption we need on the data is that they are separated, so there are no repeated data, and they're bounded. So, and they're bound. The norm of the data is bounded by this parameter capital R. So when you involve this data along the forward process, you see automatically the empirical distribution is getting smoothed, right? And this is just a plot of different the KDEs for different smoothed empirical data distribution at different forward time. And the log density ridges is basically defined for it's defined for each of this smoothed density PT. So the log density, the density ridge itself is not a new definition. It's already been used in statistical literatures for problems like classification. But as far as I know, this is the first time that people use this to analyze geometry of diffusion models. So for the definition of log density ridge, it's basically defined as the local maximum point in certain directions of these log function of PT. So for example, here I'm plotting the function log of PT with my 3-point data, and this gives you the landscape of this function log PT. And the log density ridges, for this example, is defined as this blue curve on this picture. So it's defined through these two conditions. The first condition tells you it has to be the critical point along certain directions, and the directions are defined through the bottom d minus d star eigenvalues of the hashing of the log function. And the second condition tells you it has to be a local maximum. So if you look at the eigenvalues, it has to be upper bounded by a negative quantity. And this quantity beta t is referred to as the threshold in this definition of log density ridges. And it could be manually chosen, or it could be proved for different type of density function PT. And here I'm just showcase what the log density ridges look like for different PTs. For example, when t is really small, which means the distribution is close to the empirical distribution, the log density ridges is just these two edges, right? And when you get smoother and when you get more and more noise, PT is smoother and smoother, you see the log density ridges also get smoother and smoother. And for different T, we will use this kind of log density ridges as the anchor geometry to study the inference process. And to do that, we would need to understand some basic properties of this log density ridge. For example, we have to be able to define, to show the smoothness of this log density ridge as a submanifold in the d-dimensional ambient space. And we have to show there exists a positive ridge for this manifold, so that when we have a point inside the tube within the ridge, then we can define the nearest point projection from this point to the log density ridge. So we basically prove ridge is positive, and we can define the nearest point projection within this tube neighborhood is well defined, and it's also at least C1, like continuous differentiable. And later on, whenever we have a point in this tube area of this log density ridge, we will find the nearest point on the ridge, and then we would study the tangent component and the normal component from this point to the ridge. So once we know the anchor geometry, we can study the inference process, use this anchor geometry. First, I would like to show a result, numerical result of our ridge aligned slide picture. So here we have we have M-shaped data, which are these red cross points. And we have initial data samples from the standard Gaussian. And we simulate the diffusion process in this example. Let me just switch. Yeah. So this is a simulation of the diffusion model. And you will see the general samples are evolving along the reverse process. And these green curves are the ridges for different PT at different time, right? They are evolving at the end, this ridge is getting stable, and you will see the samples are getting closer and closer to this ridge, which is a one-dimensional object in this two-dimensional ambient space, right? And they're actually getting more and more concentrated around these data points. If I play it again, so at the end, so they are trying to reach this manifold, and then they align with the manifold in the tangent space. And at the end, they slide to the data points, but they could not like slide all the way to the data points. There will be certain data that interpolate between the data points. Yeah, so this animation like briefly explain our reach align slide picture. So along the inference process, so the inference process like follow this reach align slide geometric progression with respect to this anchor geometry log density ridges. At certain points, you can show that the process will get into the tube neighborhood of the ridge. So this is what we call the reach. And after that, they will try to get aligned with this low dimensional ridge structure, which is what we call the align. And in an even later stage, within the ridge manifold, they were trying to redistribute the mass, so they slide towards the individual data points. And the analysis of our inference process is basically trying to characterize these three stages rigorously. So we start from the reach stage. To characterize the reach, we basically construct a stopping time, which defines when the inference process would enter the tube neighborhood of the log density ridge. And we were able to prove that with high probability, the process would eventually enter the neighborhood. And this probability is controlled by the early stopping error, which is this E delta. And this epsilon t is related to the initialization error, epsilon of capital T. And both these two terms can be made really small when the delta goes to zero and capital T goes to infinity. And the last term that controls the probability is the error term. So this term is actually related to the training loss. It's like this posterior mean, L2 posterior mean loss, right? If your training is done pretty relatively good, then this term can also be controlled. So with high probability, we can prove the inference process will enter the tube neighborhood. And to prove it, we basically just control the gap between the inference process, which is just red path, to the exact reverse process, which is just blue path. Because we know the blue path would memorize, so they would go to one of the data points. So by showing that this data point is close enough to the ridge at the end of the generation, and by also showing that these two paths is close in L2, then we can establish this early stopping. Like we can establish this high probability statement of the process entering the tube region. And then we characterize the reach stage. Once the inference process is within the tube neighborhood, we can try to characterize the align stage by tracking the normal component of the process. So whenever we have the YT enters the tube region, we can find the nearest point projection. And that would automatically give us a normal component of this process YT to the log density ridge manifold. And we were basically trying to quantify the square norm of this normal component and track its evolution along the inference process once the process enters the tube neighborhood. So by using um, differential geometry property of the log density region method in differential geometry, you can actually show that this squared normal distance in expectation satisfies this differential equation, whereas derivative with respect to time is upper bounded by a negative term proportional to the expected squared distance plus some remainder. And the first remainder is actually defined as the through the posterior mean difference projected on the normal space. And the other remainder can be controlled easily um, by using the property of the log density ridges, right? And this negative term is essential in order to prove the alignment statement because the scalar of this negative term depends on the rational value beta. And if you use this beta appears in the curvature definition in the log density ridges. And you can actually prove that when the number of data is finite, and if you let your early stopping time delta goes to 0, you can always choose this beta t to be proportional to c, to be of order c times 1 over ht, which is essentially c over t order when t goes to 0. And this c can be arbitrarily chosen between 1/2 and 1. And this will give you a really strong contraction at the end of the generation because the scalar here goes to infinity. So then the squared normal distance has a strong contraction at the end. So you can show that at the end of the generation, this expected squared normal distance is upper bounded by this quantity here, where the first quantity depends on the dimension and the early solving time. And because in general, you would choose the early solving time really small, so this term could be small. And the second term depends on the projected posterior mean L2 loss, right? So you project this posterior mean arrow and you scale them by constants depend on the ht function. So this provide us the quantification of the normal alignment. So eventually you can show this alignment could be small as long as the trailing arrow along the tangent direction of the log density ridges is small. Yeah, so, and the last stage, the slide stage is about the tangential direction. So to study this, we actually need to first track what is the closest center point once the inference process enters this tube region. For example, in this case, the closest point is this x01 scaled by the function at. So then we will use this as we will consider the difference between yt to this closest point. And then we approximate the tangent space, right? We want to use the tangent space at the closest point projection at this close to center, but we were not able to do that in general. So we approximate it by the tangents, using the hashing information at this closest center at x01. And we use that to approximate the tangent direction of this vector from the closest point to the inference process. And that vector is this yellow vector on this picture. And again, we were trying to track the expected square norm of this yellow tangent vector along the inference process. So we're able to establish an inequality for the expected square distance function g as the time of t, gt. So the derivative is upper bounded by a negative term, again, give us strong contraction at the end of the inference, plus a term related to some arrow depending on the posterior mean, and plus some remainder. And by quantify each of these terms, we are able to derive a tangential upper bound at the end of the inference process. So at the end of the inference process, this square norm is upper bounded by the sum of these two terms, where the first term is again depending on the dimension and the early solving time. And the second term sort of depend on the projection along some approximate tangent directions of the posterior mean. this just summarizes our analysis for this rich line slide inference stages. So we verify this analytically, and we provide a normal arrow bound and a tangent arrow bound that can tell you like how close your inference process are in expectation to the log density ridges in normal direction, and how close and how large is the tangent direction components. And we want to say this upper bounds can be numerically verified to be consistency with what actually happens in diffusion models with different training models. For example, first we test using random feature model with gradient descent optimization scheme, and we chose different weights. So the weight is constant, the weight is HT, and the weight is HT square in our training loss. And the data distribution here is simple. It's just 2 points in R2. And we're able to simulate the diffusion model under this setting with different weights. And you can see here the left 3 figures displays the generation configuration. The generated samples are blue dots. And these numbers in the box basically tells you a number of generated samples within the ball of radius 1/2 to the data centers. And you see in all the 3 settings, the configuration are on this straight line connecting these 2 data points. And the straight line here is our log density ridge. But what's different is their configuration along the tangent direction. Like in the first one, almost all points are very close to the center. In the second one, most points are close, but there are a few points that interplace between the 2 centers. And in the last one, there's no point that's really close to the center, but points are interpolating between the centers, right? And this kind of geometric behavior can be predicted by, or can be verified using our normal and tangent arrow bounds. So in the right figure, we display the tangent arrow bounds and the normal arrow bounds versus the training epochs. For the tangent arrow bounds, they are all in solid lines plotted in linear scale. The scale is on the left side of this. And you see, like for weight equals to HT, which is the orange one, and for weight equals to 1, which is the blue one, the tangent arrow bound are quite small at the end, which is reflected by the actual configuration that most of the samples are concentrated around the data points. However, for the weight HT square, you can see the tangent arrow bounds is quite large at the end of the generation. And that also verifies why in the last sample configuration, you have a lot of points that are interpolating between the 2 data points, and they are never close to the data points. And in terms of the normal arrow bounds, you can see they are plotted in log scale, and all of them are quite small. And that verifies why in all these sample configurations, you only see samples on this straight line, which is the log density ridge of these 2 data points. And similar phenomenon can be seen when you try different architecture like MLP model and trained with stochastic gradient descent. And again, you will see in this case, you can see larger generalization arrow in all the 3 configurations, but they are still interpolating between the data points. They are spreading or sliding on the log density ridge. And you can verify the difference between these 3 configurations by looking at the tangent component. So for the tangent arrow, you can still see that the tangent arrow for W equals to 1, which is this green one, is smaller than the tangent arrow for W equals to HT, which is orange one, and it's much smaller than the tangent arrow for WT equals to HT squared. So, and this again verifies that our tangent arrow bound and normal arrow bound can reflect the geometry of the generated distribution along the tangent direction and normal direction of the log density ridges. And one last part if we want to analyze this, we'll have to connect the training part to the inference part. And on the left side, I'm giving a picture that how we do it. Eventually, what we want to do is we want to analyze how the training architectures and models can affect the inference geometry. And what we can do is we can start from the bottom, which is our reach align slide inference characterization. We already have a normal and tangent arrow bound that can describe this behavior. And what we will do next is we will first connect this normal and tangent arrow bound to directional training arrows. What we did is we decomposed our posterior mean matching training loss into the tangent component and normal component with respect to the log density ridges. And we will use those two components to reflect how the training arrow affect the inference geometry. And after that, we will connect those tangent component and normal components with the architecture of the training. So for each training model and architecture, you can decompose each component into the architecture bias and the training dynamical bias. So one can show you how good your model is representing the posterior mean of the score, and the other can show you how good your optimization dynamics is finding the global minimum of the loss function. So for the first part, the arrow decomposition, we were able to show that you can, starting from the mean matching loss, you can define the normal and tangent component of it in this way. So you basically what you do is you project the difference, the vector of the difference between your learned posterior mean and the actual posterior mean along the tangent direction and normal direction at the closest point of the forward process xt. And once you do that, you can relate this quantity to the normal arrow and tangent arrow in our inference analysis. So they are not exactly the same. You can show that the normal arrow bound is asymptotically upper bounded by a scalar of the normal mean matching loss plus some remainder. And similarly, the tangent arrow bound is also asymptotically upper bounded by a scalar times the tangent mean matching loss. And the scalar depend on the early stopping time as well as the weight. And we also did some numerical experiments to show what is implicated by this upper bound. For example, we test on the same data configuration with random feature network and gradient descent. But this time, we are not reporting the normal arrow and the tangent arrow, but reporting the tangent loss component and the normal loss component. If you look at the normal loss component, you will see in this figure, they're all in dashed lines, and they're plotted in log scale, and they're all small, right? Even after you multiply the scalar, they're small. That's telling you the configuration are concentrated on the log density ridges, which is this horizontal line. But when you look at the tangent loss of three different weights, you will see the tangent loss for weight 1 is actually the largest. But as you can see in this tangent arrow upper bounds, the tangent loss itself doesn't really reflect the tangent arrow bounds. You have to multiply this coefficient. And once you multiply the coefficient, you will see that it's actually multiplied by a polynomial of delta, so which would make this loss actually much smaller. And that explains why in the first configuration, when weight equals to 1, the tangent direction arrow is actually very small in terms of from the geometric perspective. And on the contrary, if you look at the last weight, weight equals to ht square, even though the tangent loss is small in the figure, but because you have to multiply by the scalar here, if you choose weight equals to ht square, you will see this scalar is actually of order 1 over delta. So you actually need to amplify this tangent arrow in order to quantify how the tangent arrow affect the geometry in the tangent direction. And that explains why in the last one, you actually have much larger tangent bias compared to the first one. Okay, so and to further analyze how the training architecture or parameters can affect the inductive bias, we need to go to very specific setting. In our work, we check the random feature neural network where we parameterize the posterior mean by a random two-layer random feature model, and we choose the activation function to be removed. And this Wx and Wt are just Gaussian random matrix as the random features, and this A is the actual weighted parameter that we update using gradient descent. And the two key matrices in this random feature model is this kernel matrix U tilde and this vector type of matrix V tilde. So under this setting, we're able to decompose the tangent training arrow and the normal training arrow into architecture arrow and architecture bias and training bias. And we were able, for the architecture bias, we can actually represent it as directly as this projected posterior mean, but this A star is actually the posterior mean evaluate the equilibrium of the gradient descent dynamics. And for the dynamical bias, you can use the spectral information of the kernel matrix U tilde to represent it in the spectral sense. And because all the eigenvalues here of this kernel matrix are positive, so you actually can show that this training dynamical bias would decrease to zero when the training dynamics is similar to infinity. And we can plug this result to specific data configurations and to quantify what exactly are the architecture bias and training dynamical and optimization dynamical bias in different directions. For example, in the 2-point case where your 2 points are plus or minus nu comma 0 R2, you can show your ridge is always the horizontal axis. And you can show that the posterior mean is actually a vector along the x direction. And the x component is represented using this hyperbolic tangent function. And because of this, if you use the previous formula, you're able to show that the architecture bias in normal direction is always 0, where the architecture bias in the tangent direction is strictly non-zero because you have this hyperbolic tangent which would blow up when ht goes to 0. Right, and you can also represent the optimization dynamical biases, and you can see that they are decreasing exponentially fast. And you can use this expression to study the effect of the initialization of your optimization dynamics. For example, if your initialization is 0, you can show the normal component of the dynamical bias is always 0, so you have a very good low-dimensional structure at the early stage of your optimization. But if you choose different, like all ones initialization or some initialization specifically designed for slow training dynamics convergence, then you will see at the early stage, the normal direction arrow is non-negligible, and it will give you some weird geometric shape in generation. Yeah, and last, this is just some other experiments that show the relation between ridge and the generation, like the ridge of 4-point data and ridge of 3-point non-symmetric data. And we also test it on the high-dimensional data like the MNIST. And we actually like embed all the MNIST data into a 32-dimensional latent space, and we were able to track the normal direction and the tangent arrow, the normal arrow and the normal distance to the ridge and the tangent direction arrow along the inference process. And because you cannot compute the ridge explicitly in high dimension, so there are some numerical approximation going on in these experiments. But you can see the normal both arrows are decreasing along the inference process, and they will all experience a plateau at the last 200 steps in the generalization. And reflecting in the actual image generation, when we look at the trajectories along the full trajectory, the generation can start from digits 8 or 4 and then varies to generate a new digit 4 or 8. But when in the last plateau, like the 200 steps, you can see that they actually are quite stable. So that is because in the last 200 steps, the inference dynamics is already relatively close to the log density ridge, and they're just sliding around the neighborhood of the log density ridge, so that the image generated in those areas will not look quite different. So I'll wrap up very quickly. So the practical takeaways of our work is we actually provide a very concrete geometric structure oriented from the raw training data directly, and we're able to use this geometry as the anchor to provide a framework to study how the training architecture, training that parameters would able to affect the geometry of the diffusion model's generalization. Of course, there are a few limitations. For example, we didn't consider the inference discretization error, and we did not study the geometric structure, particularly within the normal space and the tangent space. And if you do this, you could potentially explain, for example, the difference between these two generations. For example, the first one here and the one here, you see they both capture the low dimensional structure, but the distribution of mass looks quite different along the tangent space. And last is there is a issue to empirically estimate or interpret the log density region in high dimension, for example. But it's still very worth to do that in practice, because once you can understand the ridge, it could help you to make a downstream task more reliable. For example, we try to visualize the ridge in the MNIST data set. We pick two data points, 4, and the first row is just linear interpolation in the latent space. You see you will have a lot of blurred force, or not necessarily can be identified as force. But once you project them onto the one-dimensional ridge, automatically you can see a lot of force with high resolution, and their written style is transiting from the left hand to the right hand. So, so if you're able to estimate the ridge and compute the ridge-related objects efficiently in high dimension, then it could be very helpful to the downstream task. Okay, that will conclude my talk. Thank you.